Antoine Lavoisier, the man who weighted the air. Paris, late 18th century. In a city that smells of smoke, sweat, tallow candles, and horse manure, one man is obsessed with something you cannot see at all: air. In a high ceilinged room filled with glass vessels, copper pipes, and strange balances, a gentleman in a powdered wig is doing something that seems almost absurdly simple. He is weighing things. Weighing metals before and after they are heated. Weighing air in closed containers. Weighing ash, water, gases, all with the patience of a watchmaker. His name is Antoine Laurent Lavoisier. He will be called the father of modern chemistry. Not because he discovered the most elements, not because he made the flashiest explosions, but because he brought a scale into the middle of the story and refused to ignore what it was telling him. Lavoisier is not born into hardship. He comes from a well-off family. He studies law, buys into a tax collecting company, marries into money. By day, he sits in offices, part of a system that will later make him very unpopular with revolutionaries. By night, he retreats to the lab he has built in his home. There, in an era when many chemists are still closer to alchemists and pharmacists, he does something quietly revolutionary. He treats matter as something you can account for. Not just conceptually, but numerically. If you burn a piece of phosphorus in air, what are you really doing? If you heat a metal until it gains a crusty calx, where did the extra mass come from? If water breaks apart, what hides inside it? Most people at the time are still working under the shadow of an older theory: phlogiston. According to phlogiston theory, when something burns, it releases a mysterious substance called phlogiston. Wood, coal, oil, metals, when they calcine, they all supposedly contain phlogiston, which escapes into the air when they burn. Fire is phlogiston leaving the material. A metal calx, in this view, is the dephlogisticated form of the metal, lighter in phlogiston. It is a neat story, it feels intuitive. It also has a problem that anyone with a good scale can notice. When you heat many metals, they do not lose mass. They gain it. The calx weighs more than the original metal. If something has escaped, why is there more stuff now and not less? Phlogiston supporters tie themselves in knots to explain this. Maybe phlogiston has negative weight. Maybe it is light, and its absence makes things heavier. You can almost feel the theory sag under the weight of these ad hoc patches. Lavoisier looks at the same experiments and sees something else. If the calx weighs more, maybe it has combined with something. Maybe that something comes from the air. And if air is doing something chemically active, perhaps air is not one thing. Perhaps it is a mixture. Lavoisier is not the only one experimenting with gases. Across the channel, Joseph Priestley is heating compounds and collecting strange airs. Fixed air, inflammable air, dephlogisticated air. Lavoisier reads these reports, repeats and refines some of these experiments, and brings one thing Priestley did not emphasize as much: the scale. He builds closed vessels, high-precision balances, apparatus where he can heat, burn, or decompose substances without letting matter escape. He designs bell jars and carefully stoppered flasks, channels gases through water and mercury, keeps meticulous records. He notices a pattern. When a metal is heated strongly in a limited supply of air inside a closed vessel, some of the air disappears, the metal gains mass, and the total mass of the system stays the same. Nothing is created from nothing. Nothing vanishes into nothing. The disappeared fraction of air is not gone. It is inside the cogs. When he decomposes the cogs again, for example by strong heating with carbon, he can recover the original metal, release a gas, and find the mass balance restored. Slowly, an idea crystallizes. Air is not a featureless, inert background. It has parts. One part supports combustion and respiration, another does not. Lavoisier isolates the active part of air, the component that combines with metals and fuels during burning and with blood during respiration. He calls it oxygen, from Greek roots suggesting acid maker, because he believes, incorrectly but understandably, that oxygen is present in all acids. The inert remainder of air, which does not support burning, he calls azote, lifeless, which will later be renamed nitrogen. Suddenly, combustion is no longer the release of phlogiston. It is the combination of a substance with oxygen. When charcoal burns, it is carbon reacting with oxygen to form a new gas. When sulfur burns, it forms a new acid oxide with oxygen. When a metal calcines, it forms an oxide. In each case, the mass increase comes from the oxygen that was in the air. He extends this logic. If we breathe, perhaps respiration is a slow combustion. We take in air, our blood takes up oxygen, we exhale air richer in a different gas. He and others identified this gas as carbonic acid, what we now call carbon dioxide. He collaborates with physicians, measures how much oxygen is consumed, and how much carbon dioxide exhaled under different conditions: climbing stairs, resting, eating. The body becomes, in his eyes, a warm, wet laboratory where combustion happens internally. Fire and life are not opposites. They are two branches of the same chemistry. From all of these experiments, from months and years of weighing, heating, collecting, and balancing, Lavoisier distills a principle that feels almost obvious now. At the time, it is a quiet bomb. In any chemical reaction, if you include all the reactants and all the products and you weigh carefully, the total mass remains constant. Matter is not created or destroyed. It changes form. Lavoisier phrases it in a way that will echo for centuries. Nothing is lost. Nothing is created. Everything is transformed. In modern terms, we call this the law of conservation of mass. It seems simple. It is also a filter. Any theory of chemistry that requires matter to vanish or appear from nowhere is suspect. Apparent losses or gains must come from gases escaping, vapors condensing, or measurement errors. If the books do not balance, check your bookkeeping. Lavoisier does not just state this as a slogan. He lives it in his experiments. He turns chemistry from a mostly qualitative art, so this powder turns green, this solution becomes cloudy, into a quantitative science. Reactions become equations. Substances get formula. Stoichiometry, the precise accounting of elements in compounds, becomes central. This is the hinge that swings chemistry from alchemy toward modernity. Lavoisier is not alone at the bench. Marie Anne Poltz, whom he marries when she is still a teenager, becomes his closest collaborator. She learns drawing and engraving so she can record apparatus and experimental setups with precision. She studies English and Latin, translates foreign scientific papers for him, including work from Priestley and others. In a time when women are often written out of scientific narratives, she is clearly present in the record, in the lab, at the table, in the margins of manuscripts. The drawings in Lavoisier's Traité élémentaire de chimie, his elementary treatise of chemistry, are hers. They show balances, furnaces, gasometers, bell jars, carefully labeled connections. These images are not decoration. They are a visual grammar for a new way of working. Lavoisier is also part of a group that proposes a new, rational system of chemical nomenclature. Instead of a chaos of traditional names, vitriol, spirits, oils, flowers of this or that, they suggest names that reflect composition: sulfates, nitrates, oxides. Language becomes another instrument of clarity. Elements and compounds get names that say what they are, not where someone once found them. For a while, it seems like Lavoisier can live a double life. By day, administrator and tax former in the Ferme Générale, part of a deeply unpopular system that collects indirect taxes for the crown. By night, meticulous experimentalist, member of the Académie des Sciences, reformer of chemistry. But Paris in the late 1780s is not a stable backdrop. Bread prices spike, pamphlets circulate, anger builds, the French Revolution erupts. Institutions that once felt eternal are suddenly on the table. The monarchy, the noble privileges, the tax forms, the academies, everything is up for dismantling. Lavoisier sees both danger and opportunity. He is involved in commissions that reform weights and measures that eventually lead toward the metric system. His commitment to precise measurement dovetails with the revolutionary desire for rational, universal standard. A meter, a kilogram, a liter. Not the king's foot or a local bushel, but his connection to the Ferme Générale, to the old regime's tax machinery, is a heavy shadow. Revolutionaries remember who collected the salt tax. Science does not erase politics. He is charged not for his chemistry, but for his role in the tax farm, with accusations that include financial abuses and conspiring against the people. He writes letters asking that his scientific work be considered, that he be allowed to continue, that the Republic might still use his skills. The tribunal is unmoved. In one oft-quoted line, the judge supposedly says, "The Republic has no need of scientists or chemists." Whether the wording is exact or embellished, the sentiment fits the climate. The trial is quick. The verdict is death. On May 8, 1794, Lavoisier is executed by guillotine in Paris, along with his former colleagues from the Ferme Générale. He is 50 years old. Almost immediately, other scientists, including Joseph Louis Lagrange, point out the loss. It took them only an instant to cut off the head. Lagrange is reported to have said, "And 100 years may not produce another like it." The revolution will eventually step back from this kind of purge, but for Lavoisier, there is no reversal. What remains is his work. The balances, the notebooks, the new language of elements and compounds, the insistence that if you weigh carefully, the universe behaves consistently. Today, if you learn chemistry in school, much of what you encounter in the first month is Lavoisier's legacy without his name attached. Balanced equations, conservation of mass, the idea that compounds are made of elements combined in fixed proportions by weight. If you take steel wool, burn it, and then weigh it, you are reenacting his puzzle with a cheap modern balance instead of a delicate 18th century one. If you trap gas from a reaction in a syringe and observe that the total mass stays the same, you are echoing his conclusion. What made Lavoisier different from many clever tinkerers before him was not just his intelligence, it was his discipline. He did not accept stories that could not survive the scale. He did not accept invisible essences that behaved however was convenient. He showed that you can make chemistry a science where numbers are not an afterthought, but a backbone. And in doing so, he prepared the way for something subtle and profound. If matter is conserved, and if compounds are made of elements in definite ratios, perhaps there is a way to talk about the number of building blocks, not just their weight. Perhaps you can count what you cannot see. Lavoisier's work leaves chemists with strong hints but unanswered questions. If water is made of hydrogen and oxygen in a fixed mass ratio, what does that really mean? Are elements continuous stuff, divisible without limit? Or are they made of discrete units? When gases combine, their volumes often relate in simple ratios under the same conditions of temperature and pressure. 2 volumes of hydrogen and 1 volume of oxygen make 2 volumes of water vapor. Why these neat numbers? Is there a hidden counting system behind the weights and volumes? Enter Amedeo Avogadro, an Italian lawyer turned physicist and chemist, living a few decades after Lavoisier, who will make a leap that sounds almost innocent. Equal volumes of different gases at the same temperature and pressure contain the same number of invisible particles. From this simple statement flows a new way to connect grams on a balance to entities you will never see directly. Molecules, atoms, numbers so large they seem abstract, and yet they govern how much gas fills a balloon, how much reactant you need in a flask, how stars fuse light elements into heavier ones. In our next episode, we will travel from Lavoisier's Paris to Avogadro's Turin. We will watch him take the measured masses and volumes that Lavoisier and others have pinned down and propose a way to count the uncountable. We will see how 1 mole becomes a bridge between the human-sized world of grams and liters and the macroscopic world of atoms and molecules. If Lavoisier weighted the air and proved that nothing is lost or created in our reactions, Avogadro will show us how to count the invisible players inside the air and gave chemistry a new unit of imagination.